Okay, so we are almost there with the new one. Okay. So what I intend to do right now is to give you an overview of the facts controllers. Uh, I described a little while ago that we will talk about thyristor-based facts, we'll talk about voltage source converter-based facts, we'll talk about HVDC, we'll talk about control coordination, and there's going to be a project based on something. So what I intend doing right now is to give you a big picture of the entire portfolio of fax devices, of the fax controllers, so that you are exposed to the basics, and then we will go into the details of each of these fax devices. Because the reason why I'm doing this is so that in the beginning itself you become familiar with all the different devices, the fax controllers, and you know what applications they are used for, so that you can decide upon the project that you want to do, and then you can continue working on the project. So rather than going serially, let's finish SVCs first, then we do StatCom, then we do this, I would just give a big picture of all the devices, all the applications, so that you get an idea about the whole spectrum of facts, and then we will go into the specifics. This might take a couple of lectures for the overview, because this is a very important material. So in power systems, where are we heading now? And this is a great change is taking in the electrical power industry. First of all, there is okay. So there's a great change which is taking in electrical power industry. The first thing that is happening is large-scale integration of renewable energy sources. We all know the story about pollution, the greenhouse gases and all of that, and we want to avoid that. You know, in Ontario they have the coal production is almost next to zero, and now it's all over the world they want to utilize energy sources which inject minimum amount of greenhouse gases, so that they are all environment friendly and still produce the same amount of power. So where do you get such kind of a clean power? They are all renewable energy sources, the wind, the sun, and other, there are a whole lot of renewable energy sources which are not such large scale, but still they are. So primarily solar and wind and solar. And then the new thing that is happening in the power systems is the implementation of smart grids. The grids are becoming smarter. Now, it's not that power engineers always consider themselves to be smart people. I mean, in 1930s they were very smart, 1970s they were very smart, 2000 they became even smarter, and now they are becoming even more smarter. So smart is always there. So what is changing? What is changing is that more and more communication is coming into the controls. There is more and more coordinated control. There is more and more communication. So you can do a lot of things with this by accessing different control devices at different locations in a very effective manner. So controls and communication. This is the main feature of smart grids. And they become more effective because the problems are more challenging and the networks are getting complex. So that is why these smart grids are coming up. So this is new, and several of these things were not understood by power engineers. You'll be surprised. We have this problem of reverse power flow, because as you know, on a feeder, let us say previously we all know that power used to go from large generating stations to the loads at the far end of the feeder. But now, this used to be the traditional story, but suddenly now there's a wind farm which has come up near the load, because the load is very close to the seashore or close to a lake, and the wind farm lies idle during the day. So power flows from the generating stations left to right to the load. But in the night, people go to bed, the load decreases, but the wind farm right at the load end peaks up. So there's a great amount of wind power production, and the power starts flowing backwards into the grid. Now, this has caused a lot of issues with the protection systems, the control systems, and the voltage issues. And you believe it or not, this has created many problems which were not understood, which were not foreseen before. So this is a new challenge to be dealt with by power engineers. And so all this is happening, which is new. So what is the goal? With all this happening, what do you want to do? You want to provide reliable power. You want power that comes 24/7. You want quality power. You want the voltage to be maintained at 120. You want the frequency to be 60 hertz or 50 hertz, depending on which part of the world you are. And you also want that there should be no harmonics, no noise, no spikes, no swells, no sags in the voltage. So this is quality power. And finally, of course, you don't want to pay for it, or you want to pay as little as you want, as you can, to get the same quality of power. So this is what is happening right now, and this is the goal. In trying to achieve this goal, there is a great need to increase the transmission capacity on existing lines. Because there is more power now, there is more wind power stations coming up, even solar power stations coming up, and the lines are still the same. There hasn't been much investment in the transmission networks for the last 2-3 decades, and the only way is that if I want to send more power, I'll have to build new lines or increase the capacity of the line. So this is a major challenge. Then not only that, you want the power to flow in specific corridors. Now, for example, think of this. Suppose the power has to come from Windsor to Toronto. So let us say, I'm just giving an example. So let's say the power has to come from Windsor to Toronto. Now power decides, so electrons decide not to listen to you. Electrons listen to Mr. Kirchhoff. They say that, okay, we will not go straight. We will not start from Windsor, cross London, cross Woodstock and come to Toronto. We like to go cross-border. So they from Windsor, they will go to Detroit. From Detroit, they will go below the lake to Ohio. From Ohio, they will go to Niagara Falls. They will have do some sightseeing and then finally climb up into Toronto. So you see, there are two paths here, and the power can flow in either path. But the thing is, you say, no, you have to listen to me. You have the power, you have to flow here because this is my territory. We don't want the power to flow in the other territory. So you need to control the flow of power, and how do you do that? So this is a major challenge. And then you want to have a reliable system even during faults. We had the 2003 blackout, and at that time, just one fault in Ohio caused a cascading second fault, third fault, fourth fault, and that kind of thing should not happen. System should still be reliable. So these are big issues, and this is possible. Now, how do you take care of all these challenges? How do you solve them? And one of the ways, now remember my finger, one of the ways of solving all these challenges is facts. It is not that facts is the only answer for solving these problems, but facts is one of the very effective methods for solving all these challenges. And you will see this is flexible, this is AC, transmission systems, this is what it is. So let me tell you what is flexible. So when you think of flexible, you think of a rubber band. You take a rubber band and you stretch it. You stretch, flex, you can stretch it. That is flexible. Or you say, well, I've got a spring. So you spring, you can compress, or you can pull it out, spring. So that is flexible. So this is flexible. And AC is alternating current. It is not DC. And this happens in transmission. So you want a transmission system which is flexible. So now you will say that is ridiculous, because suppose I give you a 200-kilometer line, how can you make a 200-kilometer line like a 400-kilometer line? You can't do that. You cannot stretch it out, or you cannot compress it to 50 kilometers. You can't do that physically. But in terms of its electrical behavior, you can make a 200-kilometer line behave like a 50-kilometer line. Or you can make a 200-kilometer line behave like a 400-kilometer line. You can do that by installing fax devices. And this is done for a certain objective, not for the fun of it, but for achieving something which is very important, and that is system stability. So the next one is, so this is the slide which talks about the flexibility of electric power transmission. what are we doing? Flexibility. This is the, so let's go one by one. The ability. So it's ability to accommodate changes. We are making some changes. Where are we making the changes? We are making the changes in electric transmission system. So we are making the changes in the electric transmission system, or we are making changes in the operating conditions. So this is what we do. This is what we understand by flexibility. And while we do this, what is it that we should not upset? We should still maintain sufficient steady state and transient stability margins. So this is very important. You have to maintain system stability. You can improve upon the system stability as long, I mean, you can do whatever flexibility in the power system as long as you ensure that the stability is the same, if not better. And the reason is that you really want it to be better. So then came the flexible AC transmission systems, FACTS. So first of all, you see AC, so look at the word alternating current. So these devices are AC devices, they're not DC devices. Now let me tell you, FACTS basically came from the high voltage DC transmission. The parent technology was HVDC. They took the principles of HVDC and in came FACTS. When FACTS came, then it became so strong that it went on its own, and it bifurcated itself from HVDC. So HVDC is not FACTS, is not a part of FACTS. That's the first thing we must know. So FACTS is AC devices. They are transmission systems. They are not distribution systems. So somebody says that, well, I put a FACTS in a distribution line. You have to question. You see, it is not really true. You may have similar controllers doing similar things, but FACTS has been defined to be for transmission systems. Okay, what does it contain? It contains power electronic based devices. So there are power electronic based devices. You can have converters. You can have thyristors. You can have diodes. You can have IGBTs, power electronic based devices. And sometimes you have only static controllers, which are not even which don't have power electronic base, but they are static controllers. And we'll talk about some of them. And the whole goal is to enhance controllability. You want to have more control in the flow of power. That is the objective of FACTS. And you also want to increase the power transfer capability. This is, yeah, Fabricio, you asked a good question. You talked about a D-STATCOM. Yes, it is exactly a STATCOM for distribution systems. So there are some STATCOMs which are now being installed. The concept of STATCOM, which came from transmission, they are installing it in distribution systems at 27.6 kV and for voltage control. So they are also FACTS devices, but the concepts are being applied at distribution levels. Yes, so you may say that is D-STATCOM a STATCOM? Is D-STATCOM a FACTS device? I would say yes, but strictly speaking, the FACTS devices were meant for transmission applications. You see, when they came in, the renewables were not there. You know, when the FACTS devices were invented, way back in 70s, 80s, and 90s, there were no renewables. There were no distribution level applications for voltage control because there were no wind farms and all of those things being connected. So they were defined for transmission applications, but now there are many distribution system applications, and the thin line between transmission and distribution is kind of disappearing. It has become very faded. So yes, they are still FACTS devices, but the basic, we must remember that the technology came from transmission and you are using its benefits in distribution systems. Does that sound okay for you? Okay, thank you. So let's move on. Now this is the limits of power flow. The limits of power flow, this is a very important diagram. Looks simple but conveys a lot of meaning. So what we have here is in terms of qualitative magnitudes. This is the biggest arrow that you see, this one that you see, this is the thermal limit of a line. So what is the thermal limit of a line? The thermal limit is the limit not at which the transmission line melts. It is the limit of the power that can flow such that, you see, there is a sag in the transmission line. Between two poles you have a sag in the transmission line, and the sag has to be above the ground, so that the people going on the ground, they are safe, or the traffic or the automotives, they are safe. So this sag cannot become larger, cannot become more. There has to be a minimum clearance distance from the ground, and the maximum power that can flow in a line so that the sag is not more than a particular limit is known as a thermal limit. And people monitor the maximum power flow in a line at the Windsor Detroit crossing. They have video cameras, and they keep recording the sag of the line. They tell you that how much power is flowing, it's more or less, that's very interesting. So thermal limit is the maximum power that you can send on a line from heating constraints. Now you feel very happy that I've got this big arrow, I can push so much power in the line. But the moment you come to the second arrow, which is a smaller one, steady state stability, the moment you try to exceed this line, exceed this much power, you find that your generators become unstable. So you say, well, what happened? I had such a large stability thermal limit, but I can't send so much power. I'm constrained by the stability of the generators. And this is steady state, mind you. That means very, very slow changes in the generator power output, very slow changes in the load. But more often, what you see are faults. What you see are line switchings. What you see are transformer trips. What you find are large load changes. And then the transient stability comes into picture. And then this limit that you are seeing is much lower than the thermal limit. This is much lower than the thermal limit. So now you can have even a worse problem. You can have a worse problem of electrical damping that has been taken care of by all the power system stabilizers. But there are countries, for example, Sweden, in Brazil, where the electrical damping of the oscillations will get damped. So the system is stable, but takes a lot of time for the oscillations to damp out. And that causes a limit on the amount of power that can flow on the line, because you don't want oscillating power on a transmission line for a long period of time. So what this picture tells us, that even though it appears to us that we have a large thermal limit, that means we can send a lot of power on the transmission line, but you are constrained by the transient stability, or you are constrained by the damping limit. This is becoming quite restricting. So what do you do? So then you say, what are my options? If I want to send from transient stability, but if I want to use the entire capacity of the line, what do I do? What are my choices? This is a big question, and this is a big question not just in Ontario but around the globe. And different solutions have been proposed, and I'm going to discuss that soon. Okay, so what do the fax devices do? The fax devices do many things. And first of all, they increase the power transmission capacity in a line. So what it means is that if you are here, so if for example the transient stability is here, the fax devices can raise this arrow from here up to this point. The fax devices can raise this arrow from here up to the thermal limit. This is what the fax devices can do if they are installed in a transmission line properly. Okay, so they can also prevent loop flows. You remember I talked about the power flowing from Windsor to Toronto, or Windsor down to Ohio through Niagara Falls back to Toronto. This is a loop flow. So the power has got parallel paths, and you would like to avoid that. So this is fax devices are one of the ways of avoiding it. That's one. They can improve the system transient stability limit. So this is another major application of FACS devices for which they are used. And then enhancement of system damping. If the oscillations are there, they are getting damped, but they take a lot of time. So then the FACS devices can increase the damping of these oscillations. Then they avoid sub-synchronous resonance. Now what is the meaning of sub-synchronous resonance? Synchronous is 60 Hertz. Synchronous is 60 Hertz and sub-synchronous means less than 60 Hertz. So we are having a resonance which is at less than 60 Hertz. This is not harmonics. This is a resonance which takes place at less than 60 Hertz, and this can damage the generator shafts. And power engineers have broken multiple shafts, which we'll talk about later. And each time they break a shaft, they open up a whole new area of research, and many people get PhDs, including myself. So we will talk about the sub-synchronous resonance and see how it can be handled by FACS devices. Alleviation of voltage instability. Voltage instability is a major problem. This is, you heard about Hurricane Katrina, which came in New Orleans. And there they are, in that area, they are installing SVCs only for the purpose of avoiding voltage instability. So voltage instability is a big issue there, and that is again possible by FACS. And limiting short circuit currents. Now short circuit currents is, I know in Ontario, short circuit currents are a major issue in GTA. And this is because the breakers are already at their limit of the short circuit current that can flow in that region. And we are trying to have more power flowing in the lines, which is coming from renewable energy sources or because of other conventional sources. So during a fault, the level of short circuit currents has gone beyond the capacity of the breakers, and it can cause big issues. It can cause, you have to upgrade all the breakers at an enormous cost, and short circuit currents need to be restricted to be able to connect more, to be able to have a safe system. And FACS devices can help in limiting the short circuit currents. Next one is improvement of HVDC converter terminal performance. Now HVDC, high voltage DC. We all know synchronous generators, power is produced typically by synchronous generators, and they produce AC power. So how does AC power become DC? AC power, you have to have a rectifier which converts AC power into DC. And the DC power is transmitted over a long distance. And at the other end, you convert the DC power back into AC power. So DC becomes AC again. You have to have an inverter. So you produce AC power, you rectify, transmit like DC, and at the far end, you take the DC and invert it into AC and feed it to the loads. So there are HVDC converters, there's a rectifier, there's an inverter. Now these inverters, they require reactive power. And their reactive power consumption can be very high. It can be as high as 60% of the rating of the whole inverter. So this reactive power is taken from the grid. And if the grid is weak, then it cannot supply the reactive power, because of which the voltage fluctuates at the terminals of the inverter. And when the voltage fluctuates, then the inverter sometimes stops working, it maloperates. So you need to do something to regulate the voltage at the inverter terminal. And that is done by FACS devices. One of the methods of regulating the voltage is FACS devices. And then another application is load compensation. Now this load compensation is primarily a distribution application, as Fabricio just mentioned, that these devices, originally the first generation of static VAR compensators, which came in 70s, a large number of them from 70s, 80s, 90s, they were used for compensating loads. That means for power factor correction, for load balancing, especially with arc furnaces and with traction loads, you see the loads were getting highly unbalanced, the voltages were getting unbalanced. So people used static var compensators to balance, to improve the power factor to unity and to balance the voltages. And they were primarily low voltage, they were medium voltage applications, not transmission level voltages, but still they were facts. I mean, they were SVCs, static var compensators. So this is a major application. This is not transmission, but I just wanted to bring it here so that you can appreciate the value and the worth, the power of fax devices. And the last one, which is the most widely being used, is the integration of renewable sources, power generating power plants. And when we talk of power plants, we are mainly talking about wind farm integrations, and we're also talking somewhat about solar power integration, those kind of things. So in wind power, I was talking to one of the major manufacturers of wind plants, and they are, I cannot take the exact name, but they come in the category of Siemens, Vestas, Enercon, in that family, in that family. And I asked them, how many fax devices or SVCs are you connecting in your wind farms? And they said at least 30 to 40 in US. And this was about 3 years back when I had this conversation. So, this is also an important thing that has to be done, which has to be accounted for by fax, and fax are largely being used for these applications. Even in Hydro One networks, there are STATCOMs which are being installed for voltage control. So the applications of fax are huge and they're enormous. So what are the compensators that we have with us? Our compensators are synchronous condensers. These are the age-old compensators, which were used for synchronous condensers. You probably know they are synchronous machines, which are operated as in the motor mode. So they become like synchronous motors. And motors are typically meant to supply loads, but these motors operate on no load. So synchronous machines operated on no load, and in such machines which are freely running, in such machines, if you change the value of the field current, if you increase the field current, it becomes the synchronous machine becomes capacitive, and if you decrease the field current, it becomes inductive. So we have those. I'm going to talk about that also. So these were the age-old workhorses of compensators or condensers, and don't think that they have gone away. I mean, they are still being used. And Hydro-Quebec has recently purchased a very large synchronous condenser for voltage for some of the voltage control applications. So that is a synchronous condenser. And then comes the fax. In the category of fax, we have thyristor-based fax. Thyristor-based fax, they could be shunt connected, then they are known as static var compensators. And so these are static var compensators which are shunt connected. And then also we have series capacitors, series compensators, which are known as thyristor controlled series capacitors or thyristor controlled series compensators. I just mentioned the name. It could be a capacitor, it could be a compensator, any one of them, TCSC. So they come under the category of thyristors. As you know, thyristors is the big brother of a diode. Thyristors, you can turn on the device, but you cannot turn it off. The current has to go to 0, then only it turns off, and then you can fire it again at a particular firing angle. So turn on is under your control, but turn off is not under your control. But suppose you say, no, I want to have the turn on under my control, and I also want to have turn off under my control. Then you go to a different generation of devices, semiconductor devices, and they are GTOs or they are IGBTs. And these GTOs or IGBTs have led to the development of voltage source converter based fax. And they have an additional degree of freedom. They can be turned on at will and they can be turned off at will. So that gives a whole new capability to the device, fax device. And here again we have a shunt connected device which is known as static synchronous compensator, the STATCOM. Then we have a series connected device which is a static synchronous series compensator, SSSC. And then you think, well, a shunt is also doing good to us, a series is also doing something good to us. How about combining both of them to get the best of both the worlds? And when you do that, you develop a composite, a unified device, and that is known as Unified Power Flow Controller, UPFC. This is very powerful. It is so powerful that there are only 3 such UPFCs in the whole world. This is very expensive, very powerful, but now you may ask me this question that why, if it's so good, why there are only 3? And why STATCOMs there are hundreds, and why SVCs are thousands? This is a question that you could ask. What I'm going to do is that I'm going to very soon I will share with you. I'm also on a working group on SVC substations, which prepares a list of all the SVCs in the world and all the STATCOMs in the world. And so there's a list of all the SVCs, manufacturers, functions, configurations, ratings, and all of that. And I'm going to post it, I'm going to share it with all of you. And then you will see, it's a very valuable document, and then you'll be able to appreciate that what all can be done and with what ratings and where it is being done. So what I would like to say is that, remember the one question, I said that you have so many problems. You have the problem of increasing power transmission capacity, you have the problem of controlling the voltage, you want to increase stability, and FACTS is one of the solutions, one of the effective solutions. Now mark my words, one of the solution. There could be many others, not many but several others. And what we want to do is that we don't want to, suppose there's a voltage we're changing, we're having a voltage problem, and we just go to our boss and say, you know what, there's a great SVC, let's buy an SVC to control the voltage. That's not the way to do it. You have to first examine all the other options which are less expensive, and you have to see whether they can meet the objective, and if only and only if the other conventional devices are not able to provide you the same objective, then you try FACTS, then you go to FACTS, because FACTS is very powerful, it's very expensive, and it has to be treated with respect. So this is what we will learn as we move along in our course. And I'm going to, just to give you an idea about, this is the last slide that I'm going to discuss today, and we will take it up further. So this is the concept of FACTS. Now what is FACTS after all? So you see, you have a line, transmission line, which has got a reactance XL, and of course in the line, you know, there are shunt capacitors, line charging capacitors, which we are neglecting for now. So at one end you have a voltage which is V1 angle delta, on the other hand, on the other side you have a V2 angle 0. So the power that flows on this line is power P12 is the product of the two voltage magnitudes V1 and V2. So product of the two voltage magnitudes V1, V2, you divide by the reactance XL, you divide by reactance and take the sine of the angular difference. So power is V1, V2 by X sine delta. This, you will be very surprised. This simple formula has led to a $2 billion industry in the world, and that is known as FACTS. This formula alone has developed the whole concept of FACTS, which is $2 billion per year industry at this time. And it looks so simple. And then you say, well, I know this formula, I learned it in my third year undergraduate studies, and how can it be so big? Well, it is very big. So what we want to do is, if we want to increase the power transfer P12, just look at this formula and say, what all we can do? Oh, we can increase V1 and V2. Very simple, you know, we can increase V1 and V2, but how much can you increase? You see, if you look at the technical interconnection rules of any utility, like for Hydro 1, the voltages can be varied between 94% to 106%, plus minus 6%, plus minus 5%. So really speaking, you don't have much room here by varying the voltages. But then you have much room if you look at Excel. And in Excel, you remember from our elementary school, our teacher said that if you divide by a small number, then everything becomes very large. So if you make Excel half, then you can make the power double. So only if you can cut this reactance into two pieces and just put one here, then the whole power can become 2 times. But obviously you cannot cut the inductance line into two pieces. There's a way to do it. So what you do is, how to decrease XL? You install a parallel line. You construct a new parallel line from this point to this point, make a new line which also has a reactance XL, and then the two impedances in parallel will become XL by 2. So if you construct a new parallel line, then basically it will, like for example between Bruce and Milton, they have a new line. By installing a parallel line, you can decrease XL. Now, by the way, constructing a new transmission line for an example between Bruce and Milton is only $700 million. So you must be so rich that you have to have $700 million to construct a line and to work with this formula to increase the power, or you can be smart and innovative. And what can you do? You can actually say that you can provide a midline. You can shunt reactive compensator right at the midpoint of the line. You can put some voltage control by using a shunt fax device. That's one of the ways. You cannot see that directly from this formula today, but we will show it to you in the next class. Or you say, well, the whole goal is to decrease this XL. We can't cut it into two pieces, but let's find somebody who is an enemy of this inductor. So, well, you say, oh, who's the enemy of inductor? It's a capacitor. So let's put a capacitor in series with this XL. So that capacitor will eat a portion of this XL, and this XL will become small. So now when I reduce my XL, then this P will become large. So series compensation is a great way. So increased series capacitor, this is another concept of which led to the series-based fax devices. And that's the second part. And then you say, well, series capacitors, so you put a series capacitor here. Fine, we put a series capacitor which reduces XL and increases the power. Great. But then these series capacitors create some problems. They're doing good. They're reducing the line reactance. You feel happy. But these series capacitors, they create a problem which is known as sub-synchronous resonance, which we will deal with later, which can break shafts. So you say, we like the capacitive effect. We don't like the capacitors. So, we like the function of the capacitor, but we don't like a physical capacitor. You see, very interesting. So then you say, well, how can we get the capacitive effect without the capacitor? This is a question. So then engineers are smart people, power engineers. So they say, okay, what does a capacitor do? Well, a capacitor creates a voltage drop, right? A capacitor creates a voltage drop which is in phase opposition to the inductive voltage drop. So it cancels a part of the inductive voltage drop. Yeah, that looks smart. So instead of putting a physical capacitor, if we inject a voltage in phase opposition to the inductive voltage drop, we have got the capacitive effect without inserting a capacitor. Correct? So this is, if you inject in the line a voltage in phase opposition to the inductive voltage, that leads to a voltage source converter based fax device, which is SSSC. And that is the third way of increasing the power flow in a line. And then the last thing, you will look at this formula. You said, well, this is a $2 billion formula. Let's see, you've forgotten about is delta. Well, delta is another way. So what we can do is we can control the delta across the line by the fax devices. So controlling angular difference across the transmission line will also increase the P12 in the line. So basic story about the entire course that we are going to now study revolves around satisfying this formula in multiple ways and designing the configurations, the power electronic structures which actually satisfy this formula and try to increase the power transfer capacity. This is the whole story of fax. how do we get different controls, how do we get different power electronic structures, and how do we use the different strategies only to increase this P12 based around this formula. That is the whole story of facts. So at this point, I'm going to finish our today's lecture, and we will meet on next Wednesday. I'm going to post this material on the course website, and at the end of the course we will have a recording. I'm going to archive this recording. This recording is being archived, and we will place it, and I will send you the instructions how to access it, and then you can listen to it at your own free time. And if you have any questions, feel free to ask us, ask Fabricio or myself, and we'll be very happy to answer. So thank you very much for this lecture. Fabricio, would you like to add anything if everything was okay? Okay. Thank you. So we will thank you, Fabricio. I'm going to stop recording.